Power series. So in the power series, we are actually going to deal with three things. We are going to start with the power series itself. Any series where the variables are in terms of powers is a power series, isn't it? Then we are going to see the Maclaurin'S series. How do we expand functions in the Maclaurin'S series? Then we are going to talk about the Taylor series. So the Maclaurin series, if you have a function f of x, it is only Maclaurin series which can expand a function f of x in ascending powers of x. Only Maclaurin series can do that. The Taylor series can expand in ascending powers of x. It expands at the point when x is equals to a, meaning it can be ascending powers of x minus 1, x plus 1, x plus or minus anything, isn't it? Then, the same Taylor series can also expand in ascending powers of h. If you have a function f of x plus h, you can also actually perform such kind of expansion in Taylor series. We are going to see all that. So the first thing, we want to see what is a power series by definition. What is a power series? A power series. So, a power series is coming from a polynomial function. We say an algebraic expression with exponents, variables, and coefficients is referred to as a polynomial, isn't it? So if you have an algebraic expression where you have a0 plus a1, remember if it is a0, the reason why I'm not putting a variable there, it is a0 x raised to power 0 plus a1 x raised to power 1 plus a2 x raised to power 2 plus a3 x raised to power 3 in that order. Are we together? So when you see an algebraic expression in this form, meaning it has the coefficients a0, a1, a2, a3 will be our coefficients. A0, a1, a2 in that order are the coefficients. Then we have x. X is the variable, isn't it? Then we have the powers. These powers 0 and the exponent 0, 1, 2, 3. Those exponents are the powers or exponents or ABCs, isn't it? So when you see an algebraic expression with coefficients, a variable, and the exponent, then it is referred to as a polynomial expression, isn't it? So you know when an expression is equated to 0, it becomes an equation, isn't it? But now, if it is equated to some function, if you look at this problem, if you look at this, you will see the variable here is x, isn't it? Meaning this polynomial expression is a function of x. Are we together? So we are saying a function of x is equals to what? a0 x0 plus a1 x1 plus a2 x2 plus a3 x3 in that order. Meaning it is a function of x, meaning it is in terms of x. Are we together? Yes. So when it is a function of x, now it becomes the polynomial function. So it is this polynomial function which we refer to as the power series. Are you seeing that? Yeah. Because you can see it's a series, it's the sum of terms is referred to as a series, isn't it? And we are saying it is power because those terms, the variables, is in terms of powers. Are we together? Yeah. So it means it is a power series. Is that okay? So the power series we've seen from this example, a power series is simply a polynomial function. Is that okay? Yes. A power series is simply a polynomial function. Now, if you look at this, if you write it in terms of summation notation, summation, we said when you are representing something in terms of summation, you simply look at what is changing, isn't it? See, summation meaning you are adding up. Are we together? So what are you adding? You are adding this term plus this term plus this term plus this term in that order, isn't it? So the addition is the summation, meaning you are summing up. And what are you summing? You check at what is changing, isn't it? So if you look at here, you are adding up. What is changing here is a0, 0, 1, 2. So you see that is changing. So you say you start from, you can use any variable, okay? You say t starts from 0, then we have or I starts from 0, then we have ai, because 0, 1, 2, 3, meaning where there is there you put I. So when I is 0, you have a naught. Are you seeing?
Yes.
Then we have our x is just the way it is. It's not changing. What is changing is this power of x. Power 0, power 1, power 2, power 3, isn't it? So it means it is x raised to power? Are we together? So you are summing up ai x raised to power I. Meaning, when I is 0, you have a naught x naught, the first term, then plus. This summation means you are adding them, isn't it? Then plus when I is 1, so you are summing from I is equals to 0 to what? Until you reach the last term, infinity. We don't know where it is ending, isn't it? Are we together? Good. So from there, this is the short form of the power series. So we've seen a power series is simply a polynomial function. Are we together? Now we want to use this polynomial function on the power series to derive the Maclaurin's series. That is the first one we are starting with. The Maclaurin's series. Let us go to the Maclaurin's series. How do we get the Maclaurin's series from the power series? How do we find the Maclaurin's series? How do we find the Maclaurin series? So we found that the power series is simply a polynomial function, isn't it? The power series is simply a polynomial function, meaning if you have f of x to be a naught x naught plus a1 x1 plus a2 x2 plus a3 x3 plus a4 x4 plus up to infinity, isn't it? So this polynomial function is the power series, isn't it? Now we want to get Maclaurin series from this. So you start here. When you look here, this is the function f of x. So when we want these values here, when x is raised to power 0, what does that imply? Anything raised to power 0 is 1, meaning this x raised to power 0 is silent, so it's just a naught. Are we together there? So it is just a naught plus a1x, x1. Are we together? So at this point, when you start here, when x is 0, at the first point, when x is 0, when x is equals to 0, what does that imply? Where there is x is 0, meaning all these terms will go to 0, isn't it? Yeah. When x is 0, you will have f of 0 to be equals to a naught. Are you seeing that? Yeah. When x is 0, where there is x, if you put 0, you get f of 0 to be a naught. Is that okay? Now let us go on. That is now the first case, maybe number 1. You move on. This is function of x. What if we differentiate this function of x for the first time? The first derivative. Are we together? If we differentiate this f of x, meaning if you differentiate a constant, you get 0 here, isn't it? So if you are differentiating a constant, you get 0. Then you go, if you differentiate a1 x1, it is 1 times a1 you remain with a1. Then 1 minus 1, so you remain with x raised to power 0. See, anything raised to power 0 is 1. Meaning if you differentiate this a1x, you just get a1, isn't it? Then it is plus, if you differentiate this 2 times a2, so you get 2s2, then you reduce the power by 1. Are we together? See, that's how to differentiate a polynomial. Then you move on, if you differentiate this term 3 times a3, 3a3, then you reduce the power by 1, isn't it? You go on, then it is plus, power times coefficient, you get 4. 4, then you reduce the power by 1, then plus until the end, isn't it? So it means we've differentiated this function of x for the first time. Then what do we look for again? When x is 0, we are looking for this point when x is 0, isn't it? So when x is 0, what is f prime of x, isn't it? F prime of x will be where there is x you put 0, so it is f prime of 0, isn't it? Where there is x you put 0. So you get f prime of 0 is going to be what? A1, all these terms with x will go to zeros. Are you seeing that? Are we together? We are done there. You move to the next one. We've differentiated f of x for the first time. Now what about if we now differentiate it for the second? For the second time, okay? So if you differentiate this for the second time, it becomes f double prime, isn't it? So if you differentiate a constant, it becomes 0. Are we together? If you differentiate 2ax, you remain with 2a2. See, this is x raised to power 1.
Yes.
So this 1 times this one, then you reduce the power by 1, you remain with x raised to power 0, which is 1, isn't it?
Yes.
So you remain with the 2a2. Then if you differentiate this, it is plus 2 times 3? 6a3, then x is now raised to power 1, you reduce the power by 1, isn't it?
Yes.
You move on, plus, if you differentiate this 3 times 4, 12a4, then you reduce the power by 1, then plus until infinity, isn't it?
Yes.
Are we together?
Yes.
So here, what do you see? When x is 0, what do we get? It implies what? Where there is x, you put 0, isn't it? So f double prime of 0 will be what? See, all these terms with x will go to zeros. So you remain with the 2a2, isn't it? Is that okay? To move on, now what about if we differentiate it for the third time, isn't it? If we differentiate it for the third time, what do we get? F triple prime, isn't it? This is f triple prime of x. If you differentiate a constant, it becomes 0, isn't it?
Yes.
Then if you differentiate 6a x1, so you remain with 6a3. Because x1 will go back to x0, isn't it? Anything raised to power 0 is 1, isn't it? Then it is plus, if you differentiate this, 2 times 12a, 24a4, then x to power 1 now, isn't it?
Yes.
Then plus until the end, isn't it? So at that point you go again, when x is 0, it implies what? F triple prime of 0, isn't it? Where there is x, you put 0, isn't it?
Yes.
F triple prime of 0 to be equals to 6a3. Are we together?
Yes.
When you do the process for the fourth time, f raised to power 4 of x, if you differentiate for the fourth time, see this goes to 0.
Yes.
Then this one is 24. A4, you remain with x raised to power 0 because it is 1 times 24 A4, which is a constant, isn't it?
Yes.
Then you reduce the power by 1, x raised to power 0 is 1, isn't it? So there plus until the end, isn't it?
Yes.
So you move again, when x is 0, what do you get? When x is 0, you get f raised to power 4 of 0 to be just 24 A4, isn't it?
Yes.
Because there's no x there, isn't it? It's just that constant 24 A4. So here you find that when x is 0, then we get, this implies f raised to power 4 of 0 is 24 A4. Now look here. We now want to make those a's the subject of the formula. Now look here, the first a is a0. What have you found to be a0? You found a0 to be f of 0, isn't it? Then what have you found to be a1? You found a1 to f prime of 0, isn't it? Then a2. What have you found to be a2? Meaning you divide both sides of the equation by 2, isn't it? So if you divide both sides of this by 2, you get a2 to be f double prime of 0 over 2. Are we together? Then you move again. What is a3? A3, it means you divide both sides of this equation by 6, isn't it?
Yes.
So you get a3 is f triple prime of 0 over 6. Then you move. What is a4? A4 means you divide both sides of that equation by 24, isn't it?
Yes.
So you get a4 is f raised to power 4 of 0 over 20 over 24. Now if you look at this f raised to power 1 over 0 is just over 1, isn't it? Now look at this. Look at this in simplest form. So f raised to power 0 is simply the same as f of 0 over 0 factorial. 0 factorial is 1. So you can see this is f prime of 0. 1 is the same as 1 factorial. Are you seeing that? Yes. Then here we have f double prime of 0 over 2 factorial because 2 is the same as 2 factorial, isn't it? Then here we have f triple prime of 0. 6 is the same as 3 factorial. Then you can see f raised to power 4 of 0. 24 is the same as 4 factorial. So it means when you don't have a derivative, it is over 0 factorial. If you differentiate it for the first time, it means you only have 1 factorial. Are you seeing? When you have 2 factorial, meaning you differentiated for the second time. Are you seeing that? When you have 3 factorial, it means you differentiated it for the third time. Are you seeing that? When you have 4 factorial, it means you differentiate for the So it means where there is A in our power series, where are A's, we are going to substitute the values of A in the power series. So if you substitute these values of A in the power series, look at your power series there. This is your power series, isn't it? Are you seeing it?
Yes.
So if you substitute the values of A in this power series, what do you see? Where there is A, you put the value of A, isn't it? So we'll have f of x is A naught, but we found A naught is just f of 0, meaning if it is f of 0, it is over 0 factorial. Then plus A1 you found is f prime of 0 over 1 factorial, then we have x raised to power 1. Are you seeing that? Yes. So you can see here x is not there, meaning when you have 0 factorial, it means x is raised to power 0, isn't it? So it means this 0 factorial can as well be silent, so that you just remain from 1 going onwards, isn't it? Yes. Are we together? Then you move on, then plus. If you have f double prime of 0, it is over 2 factorial x squared, because your A2 was f double prime of 0 over 2 factorial. So where there is A2, you put the value of A2, isn't it? Your A1 was f prime of 0 over 1 factorial. Where there is A1, you put f prime of 0 over 1 factorial, isn't it? See, we are substituting the A's.
Yes.
The values of A's, you continue here. What was your A3? It was f triple prime of 0 over 3 factorial, then your x is raised to power f triple prime of 0, then your x is raised to power 3. Are you seeing that? Now this is now what we call, this is the Maclaurin's series. This is the Maclaurin's series. This is the Maclaurin's series. The Maclaurin's series. So what is the Maclaurin series? The Maclaurin series of a function f of x, when you start from f of 0, then the next one, if you have f prime of 0, then it means you have 1 factorial, then our x is raised to power that 1. Are we together?
Yes.
Then you move the next one, when you have 2 factorial, it means you have f double prime of 0, then our x is raised to that power 2. Are we together?
Yes.
Then you move to the next one, when you have 3 factorial, it means we have then we are differentiating for the third time, then our x is raised to power this 3, then plus until infinity. Are we together? Yes. This is the Maclaurin series of a function f of x. So what have you seen from the Maclaurin series? In the Maclaurin series, it's expanding any function in ascending powers of x. If it is a function of x, meaning it is expanding in ascending powers of x. If it is a function of t, it means it is expanding in ascending powers of t. If it is w, it is expanding in ascending powers of w. Are we together? Yes. So can we now see, before we see an example, we want to see how the Taylor series is coming from the Maclaurin's series. Are we together?
Yes.
How do we get the Taylor series from that? From the Maclaurin's series. So if you look at this, if you write it in form of summations, you'll just see f of x is what? You are summing from 1 factorial. Remember, this is 0 factorial x raised to power 0, isn't it? Yes. So you are expanding from I is equals to, from I is equals to 0, you can see 0, 1, 2, 3. That is what is changing, isn't it? You are expanding f of I 0 over I factorial x raised to power I, isn't it? Then from 0 to infinity. Meaning when I is 0, you have 0 factorial f. When it is f of 0, it means you've not differentiated it. It's just f of 0, isn't it? Are we together? Yeah. It means you've not differentiated. When I is 0, your x is raised to power 0, like that, in that order. When I is 1 factorial over f prime of 0, x raised to power 1, in that order, isn't it? Yeah. That is how to represent it in summations. So this is the standard form of the Maclaurin's series, and it is only Maclaurin series which will expand any functions in its ascending powers. If it is a function of x, it is only Maclaurin series which can expand it in ascending powers of x. Are you seeing that? Taylor series cannot do that, and we are later going to see how Maclaurin series is just part of a Taylor series, isn't it? Are we together? Now from here, if you record this, If you record this, our series we found here, we want to use it to get the Taylor series. So we are going to the Taylor series. We want to use this series we derived here to give us the Taylor series. Then later, this Taylor series is now what we will use to get the Maclaurin series, because Taylor series will be general. Are you seeing that? Yeah. So we have what is the Taylor's series. How do we get the Taylor's series? The Taylor's series. So we are starting from the Maclaurin series. What have we found in Maclaurin series? If you are expanding a function f of x, then you start from f of 0, then the next, if you differentiate it for the first time, it means you have 1 factorial, isn't it? Then your x is raised to power that 1. Are we together? If you now differentiate it for the second time, then it means you have 2 factorial. Then your x is raised to power that 2, isn't it? If you differentiate it for the third time, then it means you have 3 factorial. Then your x is raised to power that 3. You proceed in that order until you reach the number of terms they want, isn't it? Yes. Are we together? Because sometimes they will tell you to expand up to the term in x cube, meaning you reach there, isn't it? You reach where they want you to reach because that series is going up to infinity, isn't it? So we go on, that is the Maclaurin series. Now we want to use this Maclaurin series to get the Taylor series. Now, look at this. A Taylor series is expanding a function at a point when, a Taylor series, in the Taylor series, it is expanding a function at the point when x is equals to a. Are we together? It is used to expand a function at the point when x is equals to a. Are we together? So when you look at this, when x is equals to a, what does this imply? This implies if you bring a this side of the equation, then you get x minus a to be equals to. Are we together? So it means when you go to the Maclaurin series, where there is x, you put not a, where there is not like that. I want to put it in another order here. Look at this. It means where x minus a is equals to 0. Now from there, look here. Here you have f of 0, f prime of 0, f double prime of 0, x like this. What is the other way you can transform this Maclaurin series? So if you look at this Maclaurin series, it is here we have f of 0, then if you differentiate for the first time, you have over 1 factorial. This x raised to power 1 can be written in the form x minus 0 raised to power 1. Are you seeing that? It can be written as x minus 0 because I want to use it. Then you go on plus the next one. If you have f double prime of 0, it means it is over 2 factorial. Then this x squared is the same as x minus 0 squared, isn't it? Yeah. Are we together? Then it is plus. If you differentiate it 3i's, it means you have 3 factorial. Then your x is raised to power 3. X is the same as x minus 0 raised to power 3 in that order, isn't it? Now, the Maclaurin series was expanding a function at the point when a is equals to 0, isn't it? Yes. But the Taylor series is expanding a function at Maclaurin series, meaning this was at the point when a is equals to 0. Are we together? Meaning the point where that 0 is, you put a, because it was at a point when a is equals to 0. Are we together? But now in Taylor series, it's at a point when x is equals to. Are you seeing that? When x is equals to a. So it means where you have x, you put a. Are we together? Where there is a, where there is 0, you put a, because a is equals to 0 in this function, isn't it? Meaning these points where you see 0, those are the values of a, because it was a point when a is equals to 0. Are you seeing? Those are the values of a. So it means anywhere you see 0, Taylor series is expanding at a point when x is equals to a. But we know we are using a series. This series we are using, it was a series when a is equals to 0, isn't it? So it means anywhere you see 0, you now put back the value of a, isn't it? Yes. Anywhere you see 0, you put back your value a. So if you put back your value a, what do you get? You get f of x is, where there is 0, you put back your value a. It will be f of plus f prime of a over 1 factorial, then x minus Anywhere you see 0, you put A, because this was at a point when A is equals to 0, isn't it? Now when we get back to our A, where you see 0, you put back your A. Are we together? Then you go plus F double prime of A over 2 factorial, then X minus A is now squared, isn't it? Are we together? Yeah. You move on, then plus. If it is F triple prime of A, then it is means over 3 factorial, then our X minus A is now raised to power that 3. You do the same when you raise it to power 4 of A, then it means it is over 4 factorial, then our X minus A is now raised to power that 4, plus, 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 until you reach the term they want you to reach, isn't it? Are we together?
Yes, sir.
Now, this is now the standard Taylor series at the point when X is equals to A. So the Taylor series at the point when X is equals to A is given by that. That is the Taylor series at a point when X is equals to A. Now, look at this. Look at this now. It is this Taylor series at the point when X is equals to A is now what we are going to use to help us get back that our Maclaurin series. Are we together? Get us back the Maclaurin's series. So we have here, if you have a function f of x, if you want to expand it at a point when x is equals to a, then this simply means if you bring a this side of the equation, then x minus a is equals to 0. So we are expanding it in ascending powers of x minus a. Are you getting that? In ascending powers of x minus a. So it means if you start from function of x, meaning you start with f of a, then after that you differentiate f of a for the first time, isn't it? If you differentiate f of a for the first time, 1 means it is over 1 factorial. Then your x minus a is raised to power that 1, isn't it? Then you move on. If you differentiate it for the second time, then it means it is over 2 factorial. Then your x minus a is raised to power that 2, isn't it? When you do it for the third time, it means you have f triple prime of a, then over 3 factorial because of that time, isn't it? Then your x minus a is raised to power 3. In that order until you reach the term they want you to reach, isn't it? So it means when a is equals to 0, then it implies Maclaurin's series. Meaning anytime you want to get Maclaurin series, you just write the Taylor series. Then when a is 0, it becomes Maclaurin's series. Are you seeing that? Yes. So where there is a, if you put 0, you get Maclaurin series to be f of 0 plus f prime of 0 over 1 factorial x raised to power 1 because it is x minus 0, isn't it?
Yes.
Then plus f double prime of 0 over 2 factorial, then x squared, because it is x minus 0, isn't it? Then you move plus f triple prime of 0 over 3 factorial, then x cube in that order. So it means it is the Taylor series which is the Maclaurin series at the point when a is 0. Are we together? At the point when a is 0. Now, we've now seen how to expand a function f of x in Maclaurin series. Meaning you can expand a function of f of x in Maclaurin series if you want ascending powers of x. Are you seeing that? You can expand a function f of x in Taylor series when you want ascending powers of x minus a. Are we together? So anytime you want to expand a case like exponential x in ascending powers of x, so that you end up with x raised to power 0 over 0 factorial plus x raised to power 1 over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus plus. So you can see these are ascending powers of x. Are you seeing? Meaning this exponential x was expanded in Maclaurin series. Are you seeing that? Because it is only Maclaurin series which will give you ascending powers of x. Are you seeing that?
Yes.
Are we together? Yes. So anytime you are told to expand in ascending powers of x, then automatically it is Maclaurin series or Taylor series when a is 0. That is the Maclaurin's series. Are you getting that? Yes. So when I hear that, expand this function in ascending powers of x, expand these functions in ascending powers of t, automatically Maclaurin's series. Now, Now that we've seen both Taylor's expansion of a function f of x and Maclaurin's expansion of f of x, now we want to see what is the Taylor series expansion of f of x plus h. Because somebody will come and tell you to expand the series f of x plus h. How does this series behave? F of x plus h. Very, very simple. So here, this is what is happening. Look here. From this Taylor series we found. This is the Taylor series, isn't it? Now, if you look at this, you are told this is at a point when x is equals to? Are we together? When x is equals to? A. But now, we now want to expand a function x plus. Are we together? So if you bring a this side, it means you have x minus a to be equals to 0, which is that our edge. Are we together? We now want to expand it at a point edge, meaning you have to remove a this side, and that it is you are expanding it at a point edge. So you remove a. If you bring a this side, you get x minus a to be now equals to at a point edge. Are you getting that? It is now at a point edge. Then after that, now see this. If you now take back your a the other side, you now get x is a plus. X is a plus. Are we together? Yeah. We add x to be equals to a. If you bring a this side, then we have x minus a to be equals to 0. So it is like saying you want to expand at a point when a is equals to 0. But now we want to expand it at a point when this x minus a is now is equals to h. Are you seeing that? So if you take back your a the other side, you get x is a plus h. So it means in this your Taylor series, anywhere you see x, you put a plus h. So we have x here. It means we are going to have f of a plus h, because x is the same as a plus h. Are you seeing that? So here we have x, we have f of a plus h to be equals to f of a, move on, plus f prime of a over 1 factorial. What is this? What is x minus a? See, x minus a we've left to be h. So it is now f prime of a over 1 factorial, then h is raised to power 1. Because anyway you see x minus a, our x minus a is h. Meaning all these x minus a, all of them are h. Are you seeing? And anywhere we have x is the same as a plus h. And where there is x is only here, we place a plus x. These two are x minus a, all of them are h. X minus a is equals to h, isn't it? Yes. So here we have plus f triple prime of a over 2 factorial, then it means that is h squared, isn't it? Are we together? Then you move, if you differentiate it thrice, f of a over 3 factorial, then it means it is over h cubed. Then you continue with the process until where you want to reach, isn't it? Because this is an infinite series, isn't it? So from here, there's now what we call the change of variables. In change of variables, we wanted to expand which function? We wanted to expand the function f of x plus h, isn't it? But look here. Here we have a plus h. What does that it means? It means a is occupying the position which x should occupy. Are you seeing that? Yes. Are we together? Yes. A is occupying the position x should occupy. So that is now the case of change of variables. Meaning anywhere we see a, we put x. Change of variables. Are you seeing that? Yes. So that instead of a plus h, we now have x plus h, isn't it? Meaning anywhere we see a, we put x in the change of variables, isn't it? So f of x plus h will be what? It will be f of x. Anywhere you see a, you put what? Are you seeing that? It will be f of x, then plus, if you differentiate f of x for the first time, then it means you have h to power 1 over 1 factorial. Are you seeing? Are we together? Then plus, if you differentiate f of x for the second time, then it means you have h squared over 2 factorial. Are you seeing that? Then plus, if you differentiate f of x for the third time, then it means you have h cubed over 3 factorial plus until then. So if you rearrange this to look beautiful, you will have f of x plus h. You are starting from f of x, then plus when you differentiate this for the first time, then plus you differentiate it for the second time, then plus you differentiate it for the third time, in that order until infinity, isn't it? So if you differentiate it once, it means you have h raised to power 1 over 1 factorial. Are you seeing that? If you differentiate it twice, it means you have h squared over 2 factorial, isn't it? If you differentiate it thrice, it means you have h cubed over 3 factorial. Are you seeing? So this is the Taylor series expansion of a function f of x plus h. Are you seeing that?
Yeah.
If you want to expand the function f of x plus h, meaning it starts at the point f of x. Are we together? So it means in power series, there are 3 important series. The first series is the Maclaurin'S series, isn't it? And in the Maclaurin series, we've seen that. In the Maclaurin series, what have we seen? It is expanding in ascending powers of that given variable, meaning at a point where a is 0. So if it is a function of x, it must be ascending powers of x. That is automatically Maclaurin series, isn't it? Then in Taylor series, we've seen you expand at a point when x is equals to a, if it is a function of x, isn't it? At a point when t is equals to a, if it is a function of t, isn't it? And we've also seen in the Taylor series, you can expand a function f of x plus h. Are we together? Now, in conclusion, what have you seen? You've seen in a function f of x plus h, start from f of x. And you've seen in the function f of x, start from f of a, isn't it? So you can design a sort of an algorithm for mastering these 3 power series. Are you seeing that? You can come up with an algorithm or a methodology or just some kind of procedure of mastering the three series. Are we together there?
Yes.
So you see, you start from the function f of x plus h to be equals to f of x to be equals to f of a. This is the algorithm I want you to use. Are you seeing that? From f of x plus h, if you eliminate h, you get f of x. Then from x, you get when x is equals to a, you get f of a. Are you seeing that? Are we together?
Yes.
So I want to show you how this is working about, okay? If somebody tells you, look here, if somebody tells you to expand a function f of x plus h, you go where f of x plus h is. Are you seeing that?
Yes.
Where is it? It is here, meaning you take this part. Meaning for you to expand f of x plus h, you must start from f of x. Are you seeing that?
Yeah.
You must start from f of x. So you come and write, you have f of x, then plus you differentiate f of x for the first time, then plus you differentiate f of x for the second time, then plus you differentiate f of x for the third time, in that order. Are we together?
Yes.
Then you put, when you differentiate it for the first time, because it was plus h, meaning we have h is what is ascending, isn't it? If you differentiate it for the first time, it means you have h raised to power 1 over 1 factorial. Are you seeing that? If you differentiate it for the second time, it means you have h squared over 2 factorial. If you differentiate it for the third time, it means you have h cubed over. Are you seeing how it is easier to get the expansion of f of x plus h?
Yes.
Are we together?
Yeah.
Then the next one you go to, how do we expand the function f of x, isn't it? So you go to your logarithm. For you expand f of x, meaning you take this part, isn't it? Are you seeing that? Meaning for you to expand f of x, you must start of f of a. Are you seeing that? You must start from f of a. So f of x you are going to have your f of a plus you differentiate it for the first time, f prime of a, isn't it? Then plus you leave some space where you are going to put those constants, isn't it? Those other things. Then you differentiate it for the second time, then plus you differentiate it for the third time, in that order. Then you now put, if you differentiate it for the first time, it means you have 1 factorial, then over x minus a raised to power 1, because it is a point when x is equals to a. If you bring a this side, x minus a, isn't it? Are we together? If you differentiate it for the second time, it means it is over 2 factorial, then our x minus a is raised to power 2. Are you seeing that? If you differentiate for the third time, it means you have 3 factorial, then our x minus a is raised to power 3. In that order until you reach a point when they want you to reach. So have you seen, you found the Taylor series expansion of a function f of x. Are you seeing? Then from there you now come and say, when a is equals to 0, you get the Maclaurin series. Are you seeing that? So when A is 0, it now gives you the Maclaurin series, f of x to be what? Where there is A, you now put 0, isn't it?
Yes.
F of x to be f of 0 plus f prime of 0 over 1 factorial x raised to power 1, because A is now 0, isn't it? So you only remain with x inside the bracket.
Yeah.
Then it is plus f double prime of 0 over 2 factorial, then x is squared, isn't it? Where there is A, you put 0. Are we together?
Yes.
Then you move on, f triple prime of 0 over 3 factorial, then x is raised to power 3. Where there is A, you put 0. So you see, this is the Taylor series expansion of a function f of x plus f. This is the Taylor series of the expansion of the function f of x. Are you seeing that?
Yeah.
Then this is the Maclaurin's series expansion of a function f of x. So you can see the Maclaurin series is ascending powers of x. Are we together? So that is all about the power series. Now we want to do examples in each case. How do we expand functions in the Maclaurin series? How do we expand functions in the Taylor series? How do we expand functions in? How do we expand functions in all those given series? So let us start with example number 1.